Right, so okay, so let's start. So this is Math 505 differentiable manifolds. Okay, so what we will do, efendim? Olur, olur. So we start with the definition of manifold. Uh, okay. First, we say what's a topological manifold? A topological manifold uh, is a Hausdorff second countable second countable space, topological space uh, with the following property. What's that? Each point of the space, maybe I should give a name, let's say M. Each point P in M has a neighborhood uh, U. So this U contains M, P, and contained in U, and a homeomorphism. And there is a homeomorphism. Let's say phi from U into V, where V is an open subset of some Euclidean space Rn. So what is a topological manifold? It is some topological space, let's say M, so that it is Hausdorff and second countable okay. Sorunu anladım. Şurada bir şey sorunu var da. Okay. Ekranın dokunmatik özelliği de var. Onu turn on yapmıştım bir ara. Unutmuşum. Elim değdikçe şey yazıyor. Kalem gibi. Onu fark ettim. Kusura bakmayın. So there is for each point P there is some open set U here and the homeomorphism uh, onto an open subset in some Euclidean space Rn. Okay, Rn has the standard topology, and M has the its given topology, whatever that is. And for each point, we should have such a homeomorphism. Okay, this means that a manifold locally looks like Rn, right? Because whenever you pick a point, it has a neighborhood, and that neighborhood is an open subset of Rn. So when you look around, you see just a copy of Rn. Okay. However, M has two more properties that it has to be second countable and Hausdorff. These two properties are important because of the following practical fact actually. Usually we would like to see manifolds as subsets of some Euclidean space, okay? Like surfaces or curves in 3 space or in 4 space. And Rn is both second countable and Hausdorff. And therefore, any subset of Rn has to be second countable and Hausdorff. So if you want your manifold to be a sub manifold or subset of some Euclidean space, it has to be Hausdorff and second countable to start with. Otherwise, there is no way you can regard your manifold as a subset of some Rn. Okay, is a subspace of some Rn. And it turns out that these two properties, that being Hausdorff and second countable, is indeed enough to embed your manifold into some Rn so that it becomes a submanifold of some Euclidean space. Okay, we will come back to that later, but for the time being, so we should keep in mind that manifolds are topological spaces which are both Hausdorff and second countable, and more importantly, every point has a neighborhood so that that neighborhood is homeomorphic to an open subset in some Euclidean space. Okay. By the way, I didn't ask you, but does everyone knows topology? So, like, what's a Hausdorff space? What is second countable space, and so on? Yani aranızda topoloji bilmeyen var mı? Second countable, efendim? Tamam. Second countable şey demek, topolojinin bir bazı var. Bazı countable. E, Yani bu da ne demek? Topolojinizin open setleri bir tane countable bir küme içeriyor. Ve bütün open setler de o countable kümedeki elemanların union'ları şeklinde yazılabilir. Countable bir basis'i var yani topolojinizin. Hı hı. T1 yani evet. Evet, evet. Locally Euclidean olup Hausdorff olmayan uzaylar var. Aha, evet. Peki, e, şimdi kitabın şey notasyonu biraz e, benim alışık olmadığım. E, Şimdi şöyle bir şey var. Elimizde diyelim ki iki tane yani bir noktayı içeren iki tane open set olsun. Assume that P is in U1 intersection U2 and this is from U1 to V1 and psi from U2 to V2 homomorphisms where V1, V2 are open subsets of Rn. Yani elimizde şöyle bir resim var. We have our manifold. Okay, let me write it like this. And we have two open neighborhoods like this. And we have phi, let's say V1 and then psi, and here V2. And we have this intersection. Okay, so that is U1 intersection U2, this intersection. And image of this intersection under these homeomorphisms are some subsets like this, let's say, and like this. Okay, and here I have the composition map. What's that composition? From this, intersect image of the intersection. So this thing is what? Belki onları da yazayım. This is image of this intersection, and this one is psi of U1 intersection U2. And here I have the composition. Since these two maps are homeomorphisms, their restrictions to some open sets are also homeomorphisms onto their images. So I can go up by the inverse of phi and come down with the homeomorphism psi. So I have this map, and this is also a homeomorphism. Why is that? Because both of these maps are homeomorphisms, therefore the composition is also a homeomorphism. Okay, so whenever you have two open two coordinate systems or charts, this composition will be a homeomorphism from an open subset of Rn onto an open subset of Rn. Here, actually, I am a little bit cheating. You may, object to the following. In the definition, we say that each point has a neighborhood which is homeomorphic to some open subset of some Euclidean space. Suppose this is a Euclidean space, let's say Rn, and this is another Euclidean space, but it could be maybe Rm, right? In the definition, we didn't say that n and m are the same. And it is not clear right away that y and mn should be the same, right? So here one should prove the following. An open subset of Rn, if it is homeomorphic to some open subset of Rm, then n should be n. Okay? N and m should be the same. That is true, but not easy to prove. Okay? It's not easy to prove. It needs, if you only work in topological category, so with continuous maps, homeomorphisms, and so on, you need either homotopy groups or homology theory to prove this. So it takes a lot of work. But if you work with smooth maps, which we will differentiation and so on, then many things can be translated into linear algebra, and in linear algebra you just compare dimensions of vector space and life is more easy there. And we will see immediately that R should be equal to M if this is a differentiable manifold. But at the time being, actually it is not clear, okay? However, we know that it has to be the case that N and M should be the same, okay? Yani N'nin M'ye eşit olduğunu biliyoruz ama hani ispat et derseniz şu anda topolojik olarak ispatı kolay değil. Yani o homoloji teori gerektiriyor. Ama sumut kategoride ispatı kolay. Dediğim gibi onu yapacağız. Şimdi evet bir tane daha definition var. Bu topological manifold'un definition'ı. İsterseniz şuraya remark olarak şunu da yazayım da. Remark. Any subspace of the Euclidean space is both Hausdorff and second countable. Uh, Indeed, we will see later. Any manifold is well, actually homeomorphic to a subspace of some Euclidean space. Okay. This is one remark. So therefore, it is better to start with a second countable and Hausdorff space. Okay. Otherwise, there is no hope that your manifold will be a subspace of some Rn. Actually, the second remark is also related to that. Consider the quotient space, so-called the double, real line with double origin. Consider the real line with double origin. You probably have seen this if you took any topology course. What is this this space? It is the following. You take two copies of real line, okay? Let's say one copy with for -1 and one copy for 1, and you identify all the pairs of points x comma -1 with x comma 1, provided that x is not 0. So what you do, you take two copies of real line, okay, like this. So this is r cross, let's say 1. This is r cross minus 1. Identify means you just, glue those 2 points. And here we are asked to do so uh, for each x, right? For each x here, x comma 1 and x comma minus 1. So for each x, I will identify these 2 points. So this is x comma 1, this is x comma minus 1. I'll do this for all points, y comma 1 and y comma minus 1, except the origin. Therefore, except the origin, all these pairs of points become 1 point, but I will have still 2 different origins. So my space X is something like this. It looks like this. I have a real line, but it has 2 origins. Okay, 2 origins. That's why this is called a real line with double origin. This space is not Hausdorff. Okay, X is not Hausdorff. Is not Hausdorff, but it is locally Euclidean. So locally Euclidean. In other words, every point has a neighborhood which is homeomorphic to some open interval in this case, because we are in one dimension. What are those intervals? For example, if you are at this point, then this point has a neighborhood U, which is a copy of a interval in R, right? So this is just an interval. So this point has a neighborhood which is homeomorphic to some open subset of real line. What about this point? Let's say this point. This point has also a neighborhood which is homeomorphic to some uh, re open subset of R. What is that? Well, actually, it is nothing but image of this. Okay, image of this. So it's something like this. I have this point plus these 2 half intervals. It is the copy of this open interval. It is homeomorphic to this open interval. So this point, this origin, one of the origins has a neighborhood which is homeomorphic to some open subset of R. What about the other one? Well, this point also, this point or this point has also some open set around it, which is homeomorphic to some open subset. It is just image of this one. So what is that? It is this point plus these 2 intervals again. Okay, the same intervals, half intervals, together with this point. Okay, so every point has a neighborhood which is homeomorphic to some open interval. And actually you see that why this is not a Hausdorff space, because you cannot find 2 open subsets which separates the blue point and the orange point. Okay, any 2 intervals containing these 2 points has to intersect. Okay, that's why this space is not Hausdorff. You cannot regard this as a subspace of any Euclidean space. So we will not consider this object, although it is locally Euclidean, uh, as a manifold. Okay, this is not a manifold for us. But there are some generalized objects. Uh, there are some texts where this kind of spaces are called non-Hausdorff manifolds. Okay, so there are some, you can actually study this kind of objects also. I mean, they have some uh, similar properties analogous to honest manifolds, but because of this non-Hausdorffness, things are complicated. Okay. Uh, okay. But you cannot avoid this kind of stuff. Okay. They just pop up everywhere. Even if you study smooth manifolds, Hausdorff ones, it turns out that you may have to deal with this kind of stuff. Even I guess in physics and in engineering, there is this Hausdorff business. I saw some articles about non-Hausdorff materials. Okay, material science people, I guess, are studying. Probably it is related to uh, orbits of electrons. This is my guess. Probably something like this. Okay. Now, what about differentiable manifolds? Here is the definition. Uh, we will say that uh, u phi, this coordinate system, and another coordinate system v psi r, c infinity compatible, ya da şöyle diyeyim ya, u1 phi and u2 psi diyeyim. Bu notasyonu kullandık. C infinity compatible if u intersection v if non-empty implies that uh, the compositions şöyle biriyle gidip diğerinin tersiyle dönüyoruz. Yok. Şöyle olacak. Are both smooth uh, functions. Smooth functions means they are infinitely many times differentiable. Yeah, they are infinitely many times differentiable. That is, of course, equal to the following. So these are both functions from some Euclidean space into some Euclidean space, right? Like this one. So I have this composition, and the other composition is like this. Okay. So it's from some Euclidean space into some other Euclidean space. What we mean by saying that this function is C infinity, I look at each coordinate function of the, this compositions, and those coordinate functions has to be C infinity. In other words, all of its partial derivatives of all orders has to exist. Okay, so you should be able to take derivatives as many times as you want. All the partial derivatives should exist. If all the partial derivatives exist of all orders, then these functions are infinitely many times differentiable. Okay. Peki şimdi burada şey gördük. İki tane koordinat sisteminin C-infinity compatible olması ne demek? Eğer bunların tanım kümeleri kesişiyorsa kesiştikleri işte yerin imajları arasındaki kompozisyonların C-infinity fonksiyonlar olmasını bekliyoruz. Ee, C-infinity manifold ne peki? Ya da structure şöyle diyeyim. Differentiable nasıl? Evet. Ha. Buradaki notasyona tam uymadı değil mi? O zaman şöyle yazayım ben. Şurada tekrar yapayım onu. Şöyle diyeyim. Evet burada şöyle diyeyim. Tekrar şimdi manifoldumuz bu. Topolojik manifoldumuz. İki tane diyelim ki bu locally Euclidean olma koşulunu sağlayan koordinat sistemim var. Bir tane map'im şu. Diğer map'im bu. İşte bu bir Rn'deki bir open set'e gidiyordu. Bu da Rn'deki bir open set'e gidiyor. Bu ara kesitin görüntüsü burada. Bu da burada. Şuradaki map işte şu. Bunun tersi de var. Bunlar homeomorfizm olduğu için kompozisyonlar da homeomorfizm. Artık bunlar hani array'nin bir open setinden array'nin bir open setine gidiyor. Dolayısıyla da yani elimde şöyle bir şey var. Burada diyelim ki ben koordinat sistemi seçtim. X1, Xn. Burada da koordinat sistemi seçtim. Y1, Yn. O halde bu fonksiyon işte X1, Xn ni koyduğumda işte n tane koordinatı var. Diyelim ki bunların koordinatları şey olsun. H1x yani tabi x değil aslında x1, xn nereye kadar? Hn, x1, xn diğeri de şu olsun. Y1, Yn the G1, Y1, Yn Gn, Y1, Yn ne istiyoruz? Bütün bu hi'ler ve gi'ler all hi's and gj's are okay, are C infinity. Yani o da ne demek? H'in ve G'nin istediğiniz kadar şeyini alın, türevini alın. Bütün türevleri var. Eğer boş küme değilse bunu istiyorum. Boş küme ise zaten kontrol edecek bir şeyiniz yok. Non-empty non-empty ise işte bunu istiyorum. Ha. Tamam. Pardon. Anlaşıldı mı? Yani burada H ve G'nin de bunlar Rn'den R'ye giden fonksiyonlar. Bunların da sonsuz kere türevlenebilir olmasını bekliyoruz. Yani işte H'in Diyelim ki herhangi bir k. türevini alıyoruz. Del xi1 del xi2 del xik. And bunun da del y j1 del y j2 j y k exist for all. Yani bütün partial derivatifleri exist olmalı. Peki şeye gelirsek okay. A differentiable or C infinity or smooth. So all these terms are used. Differentiable manifold, smooth manifold, C infinity manifold. They all mean the same thing unless stated otherwise. Structure on a topological manifold M is a family U, let's say, and family consists of U alphas and phi alphas of coordinate neighborhoods such that so what we mean by a coordinate neighborhood is a this locally Euclidean structure, right? U is a open set in the manifold, and phi is a homeomorphism from that open set into onto some open subset of some Rn. And we ask the following: these open sets cover M. So the collection U alpha cover M. Ne demek? Yani M bunların union'una eşit. İkincisi de for any alpha beta in the index set of this family, the neighborhoods uh, are C infinity compatible. In other words, if U alpha and U beta intersect, if the intersection is non-empty, then the two compositions we considered above are C infinity maps, okay? So going from one coordinate system to another one should be a smooth operation, okay? Third, any coordinate system any coordinate neighborhood, neighborhood V psi compatible with every U alpha V alpha of this family is itself in U. So this is kind of a maximality condition. We will call this collection of neighborhoods as C infinity structure if it is maximal in that sense. Okay, so this open set should cover the manifold, and the compositions from passage from one coordinate system to another one should be smooth. And finally, this third condition tells us that any other uh, coordinate neighborhood which is compatible with all the elements in that collection must be also in that collection. In other words, this collection should be a maximal one. Okay? If we have such a collection, then we will call this a smooth structure or a differentiable structure on the topological manifold. A C infinity manifold is a topological manifold together with a C infinity differentiable structure. Okay. Let me make two remarks. Uh, Not all topological manifolds admit a smooth structure. Okay. Not all topological manifolds admit uh, a smooth structure, C infinity structure. So there are some topological manifolds, but there is no smooth structure on that manifold. Okay, you cannot put a smooth structure. In dimension 1, 2, and 3, there are no such examples, but in dimension 4, things get weird, and there are topological manifolds which do not admit any smooth structure. Okay, topologically they look like Rn, they embed into some Rn, but they are not differentiable manifolds. They don't admit any differentiable structure. Second remark is that a manifold may admit, a topological manifold may admit more than one non-equivalent smooth structure. A topological manifold may admit different C infinity structures. I said different, but I'll come to this, what we mean by different, okay? What we mean non-diffeomorphic. They are homeomorphic, but not diffeomorphic, okay? Uh, this was first observed by şimdi Milner, John Milner in 60s, and till him nobody knew that there is a distinction between smooth and topological manifolds. People thought that any topological manifold has a smooth structure, and this smooth structure has to be unique. Okay, because it was like this in dimension 1, 2, and 3. Milner constructed spheres, 28 of them. All of them are homeomorphic to the 7-dimensional sphere, but they are non-diffeomorphic. Okay, he showed that they are non-diffeomorphic, and that work is considered as the birth of so-called differential topology. Okay, because differential topology and uh, topology of study of topological manifolds uh, became different subjects after his work. And in 80s, we learned that R4, and it is the only Euclidean space, has uncountably many different smooth structures. They are all homeomorphic to R4, but smooth as a smooth structure, they are all different, and we have uncountably many of them. Okay, so these were surprising facts, and showed that the study of smooth manifolds is quite different than the study of topological manifolds. Okay, all right, let's have a break.